Hi everyone, today I'm going to be talking about Sudoku solvers. I'm going to try to keep this video short and to the point, and I will try to keep the code as simple as possible, which is why I've chosen Python. Now, there are 1 million Sudoku puzzles in a Kaggle dataset. So if you want to write your own solver, I recommend just downloading that dataset and making sure your solver passes all 1 million cases. If you can pass all 1 million cases, you're probably good. However, there are 20 impossible cases I found, like impossible for humans to solve. So it would be good to test those as well, because it will really test like if your algorithm has been like implemented well. It will test how fast your solver is. Okay, so I'm going to start by explaining the algorithm like intuitively, and then I'll start writing the code for it. So here we have a board. I've chosen a pretty simple board, probably like we would consider this to be like an easy board. For example, let's look at column 7. And as you can see, well, there's an 8 in this column. There's an 8, sorry, there's an 8 in this row, an 8 in this row. And this column does need 8, and there's only one square left that 8 could go, so this is an 8. This column also needs a 4 and a 7. So one of these squares is a 4 or 7, one of these squares is a 4 or 7. So imagine we go through each box in our board, and there are 9 boxes. And for each box, we write in the top left-hand corner every single number that could go in that box. So for example, for this square in this box, there could be a 2, a 3, or a 6. And then we do that for this box, like this square, this square, this square, this square. Now we've done it for every square in the box. We do that for all boxes. And then what we're going to do is check like how many of these squares have a 2 in them. Maybe only this one has a 2, and then we know, well, because this one has a 2 and this box doesn't have a 2, then this one must be a 2. This is kind of the strategy. So first, you figure out what numbers can go in every square. Then you know that because this box needs to have every number, and like one of the numbers can only go in this one out of the 4 squares, you can solve the number. We're going to do that for all of the different boxes. And then suppose we solved a few numbers along the way. Like for this strategy, we were to solve 3 numbers. Then we're going to go through the entire board again, do the entire thing again. And eventually we'll reach a point where we didn't solve anything. At that point, we're going to have to make a guess because we're stuck. And we will make a guess and then continue solving. And it's possible that our guess is really good and we're able to solve the whole board just using the strategy I mentioned. And if we get stuck, we're going to have to go back to that guess that we made and change it. Like it was a bad guess. Let's use the other number. Like maybe here there's a 4 or a 7, so we guessed 4, but 4 was not right. The square was actually a 7, so we guessed 7. Then we go and solve, and then it might work. So you have to consider this sort of backtracking logic. All right, this is the basic idea. So let's get into the code now. So first, I'm going to implement the solve function, assuming we have some strategy. So let's start by copying the board. We're going to define some root node. Like so. I will explain what all of these different parts are. So the root node is associated with this board. It doesn't have a parent since it's the root. It doesn't have a child yet, but it might have a child. It's depth 0 just because like it's the first node, and we haven't made a guess yet. And this value is just associated with the guess. So for the guess, I store like the row, column, and then all of the possible guess options. So for example, this is row 2, column 7, and all the guess options would be like 4 or 7. So that would be our guess, and the value would be whatever value I choose for the guess. For example, 4. Okay, so let's start. So we're going to go through this loop. So we're going to apply the solve strategy I described, which I have not implemented yet, but I described it, where the solve strategy involves going through the entire board, going through every square, looking what numbers could possibly go in that square. Then after you've done that, going through each of the boxes and solving any of the entries that you can. This is our strategy. We're going to apply this strategy as many times as we can until we reach one of these states. The possible states are we've either solved the whole thing, in which case we're done, return board, or we're stuck, which I will be going through in just a sec, or we have failed. These are the three possible things that could happen. So let's go through the stuck one. If we are stuck, let's create a copy of the board, because we keep changing this board, and at this point we have there's a possibility we could just damage the board and repair if we make a wrong guess, and we're going to need to roll back to this board. So we need to copy it here. Now we're going to have a child for our current node. It will use the current board. The parent will be the current node, and the depth will be whatever the current depth is, which in this case starts at 0, and then +1. So let's put that onto a new line. And okay, so now that we've created the child, we're going to set our current node to the child node, and we are going to get a guess. Now, when we're getting this guess, we should really get a guess for a square that we are kind of close to. Like, if there are three possible numbers for this square, like we know the square is either 2, 3, or 6, that would probably not be a good square to make a guess in, because we probably have some other square where there's only 2 possible options. So we kind of have like a 50-50 chance of getting the guess right. Here, if we guess, we only have like a 1 in 3 chance of getting the guess right. So when we do this guess, we should be like a little smart about how we actually guess. Although any of the squares which have like 2 possible, any of the squares which have like 2 possibilities is probably a good square to pick. It probably doesn't really matter which one of those squares we pick. And then we're going to actually like choose one of the guess options. So in this case, I'll just choose like the first option. Then we're going to apply the guess, which basically means to, like here, our options are guessing between a 4 and a 7. So we decide let's guess 4, and then we're actually just going to literally fill in a 4 on this board. That's what this apply guess will do. Oh, sorry, I already did that one. All right. Very good. So now we've applied a guess, and then we're going to go back through the loop. So we've applied this guess, we're going to apply our solve strategy again. If the guess was correct, we will successfully solve the board and we'll be done. If we get stuck again, we will have to make another guess, which will involve setting, we will go one level down, like our depth will increase by 1, and we will make another guess and apply that guess to the board and try to solve again. If we fail, this will only happen if, for example, we made a bad guess. Then we need to change our guess. So let's just ignore this part for now. So, okay. So let's assume that we're in the scenario I was talking about. So we have made a guess between a 4 and a 7. And we guessed 4, and 4 was not the correct number. So we want to change our guess to 7. So how can we do that? Well, the basic idea would be that our guess options originally we used option 0, right here. And now we know option 0, that was a bad guess. Like, no point keeping that one as an option, so we remove it. Okay, so when we're taking 1 to whatever, we've removed option 0. And now we are going to make a new guess, which is just going to be the new, option 1, which is now option 0, because we've removed the previous option 0. Okay, so we've changed our guess. So initially we guessed 4, now we're going to guess 7. We're going to apply that guess to the board. And we are good. Now this will work if, oh, sorry, one other thing. So before we do this, we have to roll back to the previous board. So we have to essentially do this. Whatever the current board is, we have to roll this. This is rolling back to the previous board. Okay. And but one problem that you might run into is you guess this one is a 4 or 7, this one is a 4 or 7, and you try 4 and 7, and neither of them work. That could happen if you're like many levels down, and you made a previous, like a bad guess, a few levels up. So what you actually have to do is check, are there any options left to try for this particular guess? And as long as there's at least one option left to try, you're good. But if there isn't, you need to go up a level. So this code is meaning go up a level. All right. So this is the entire backtracking algorithm. So let me just reiterate it one more time. So we apply the solve strategy. If it solves, we're done. If we get stuck, we're going to make a guess. We're going to save the previous board in case we need to roll back to that board. We're going to apply the guess to the board, and we're going to try to solve again. If that guess was correct, we're going to be solved and we're done. If we get stuck again, we need to make another guess, and we're going to keep going down levels, making guesses. If our guess is ever incorrect, we will end up in this failed state, which will mean that we will try a different guess. And if we've tried all the guesses and there was something wrong at this level, we go back up a level. That's the idea. Okay, so now I'm going to focus on the solve strategy thing, which I was talking about. So let's keep a copy of the board. Now why we're going to do this is because we're going to try to fill in, we're going to try to solve some entries, and then we're going to check. This will modify board. And then if board is equal to the initial board, like we went through the entire board, we scanned everything, we weren't able to solve anything, we are stuck, we return stuck. Okay, that's why I kept a copy of the board. Right, so regarding this solve strategy, like I mentioned, I'm going to go through each of the 9 boxes, and we are going to fill in the missing entries. So I mean like right in the top left-hand corner of each, or like right for each square, all of the possibilities. So this one is a 2, 3, or a 6. We're going to do that for every square in the box. And then we are going to solve the missing entries in that box. So this part will be like I was mentioning, we know that this square has a 2, and none of the other squares have a 2. So if only one of these squares could have 2, then we can solve it. We can solve that square. That's what this part will do. Okay, and so we do that for all 9 boxes. And now we want to check. This part is basically like check if the board is solved. So let's assume that it's solved, and if we find any evidence otherwise that it's not solved, then we will set solve to false. So for example, so here, if the length of the board is actually greater than 1, then solved is false. because that means that there is a square, such as the square, where there are still two possibilities for that. And because there's two possibilities, we can't be sure, and we haven't actually solved the board. So solved is false. If we find an entry where there are no possible numbers that could go there, this means that we have failed. Like we made a bad guess and we have failed. We're going to return failed, and we're going to go back to that thing I was talking about before, where we need to try a different guess. Okay. If after all of this we didn't find any problems, we have solved the board and we return solved. This is the idea. And one scenario is you go through, like a very common scenario is you go through all of the boxes. You were able to solve a few entries, but like there are still some unsolved entries, so solved is false. So what you should do in this case is you should actually keep performing this solve strategy over and over and over until you either get stuck, until you get failed, or until you're solved. Okay, so I'm gonna implement the the fill in missing entries first. Let's do that. So box here is like the box number. So like it's like 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So one thing we need to do is we need to figure out like what are the rows and columns which define a box. So here, this box is like bounded by row 0, row 2, column 0, column 2. This box is bounded by row 0, row 2, column 3, column 5, and so on. That's what we're figuring out here. So if the box is one of these boxes, then the rows are 0. Like if it is one of these three boxes, then the row is 0 and 2, and so on. Okay, and similar thing for the columns. So if the column, if the box is 0, 0, 3, or 6, then it will be column 0 and column 2. And if the box is 1, 4, or 7, then the column will be 3 and 5. Okay, and so on. Okay, so now we're going to loop through every square in the box. And this is the square. So if there's only one number in this box, then there's nothing to, like, we don't need to fill in numbers in the top left-hand corner, right? So if we're encountering this 7 square, there's only one number here. Like this square is already solved. We shouldn't fill in anything. Okay, so let's continue. Otherwise, we want to get the possible values for this square. Now, so this get possible values thing, so initially the possible values could be anything, right? For I in range 9. So it's like 0 to, it should actually be I plus 1. Okay, so this will be like 1, 2, 3, 4, 5, 6, 7, 8, 9. So so we're going to go through, okay, so what we want to do here is we want to know what are the possible values for this square. So we need to scan the row, we need to scan the column, and we need to scan the box. So here, when we're going like board of row and I, this is going to scan the entire row. Like we're going through all of the columns in this row. Okay, so like we're literally going through this square, this square, this square, this square, this square, something like that. So if this particular square, like for example, we get here, and the length of like this square is already solved. So then the length of this square will be 1. That's the kind of scenario. So then, if this is the case, then that would mean that we're trying to figure out what numbers could go in this square. Well, so we're scanning this row and we found a 7, so we know definitely there can't be a 7 in this square. And like similarly, we're going to scan this column and we see, oh, there's a 9 here, so there can't be a 9 in the square. And then we're scanning this box and we see, oh, there's a 8 in this box, so there can't be an 8 here. And at the end of after we've done this, we're going to be left with a few numbers that could still be here. So this is scanning the row, and it's removing all of these. So we start with numbers 1 to 9, and we've removed numbers 7 to 9, 3. None of those numbers can go here. Then we're going to do the same thing for the column, and then we're going to remove 9, 8, 5, 4 from here. So this code here, this will go through the column. Okay, and then going through the box is a little tricky because you actually have to loop like this. You need to like go 1, 2, 3, 1, 2, 3, 1, 2, 3, kind of like a zigzaggy thing. So for this, what you can do is here's how you can do it. So I divided by 3. So you can imagine if I is 0, this will be 0. If I is 1, this will be 0. If I is 2, this will be 0. So that will achieve this sort of pattern. 1, 2, 3, and then you are going to flip rows. Okay, and this will achieve your column thing, right? So if I is 0, you're going to be in column 0. If I is 1, you're going to be in column 1. So this will achieve the pattern for looping through the box. So okay, so we've done what I described. We figured out what possible values can go in the square. We're going to return that possible values. That completes this fill missing entries thing. We still have to do the solve missing entries thing. Which, as I was mentioning, is we know all the possible entries for this square, we know all the possible entries for this square, and then we're going to see how many of these squares have a 2 in them, and if only one of the squares has a 2 in them, then we can solve for the 2. That's what we're doing here. Actually, this is the same logic here, so I'll just copy it. And actually, this loop is the same. Okay, so we are going to do exactly what I said. We are going to keep track of which squares can hold each number. So this is saying, what are the possible squares that a 1 could go in? What are the possible squares that a 2 could go in, etc. So if there is only one possible square, so maybe I'll call this this is kind of like the number, right? So if there's only one possible square for this number, then we can go ahead and solve this number. Sorry, this is number. Right, so for example, if there is only one possible square where 2 could go, and this entry has not yet been solved, we will update it. We will solve that entry. So this solves the entry which was previously unsolved. Okay, so what have we done here? We have this is done. This is done. So this whole thing is done. And so our whole solve strategy has been implemented. So I think all that is left to do, let me just double check that. Yes. Okay, so all that is left to do is figure out how we are going to get the guess and apply the guess. So this part. Actually, getting the guess isn't actually, like, I do something that maybe you would consider is a little complicated, but the idea is pretty simple. Like, we have gotten stuck, and for each square that is unsolved, there is like 2 or more numbers that could go in that square. So technically we could just take any of the unsolved squares and use that as our guess, but what I want to do is like figure out which square has like the fewest number of possibilities. Like probably 2 possibilities would be ideal, and then use that square as our guess. So there is probably a simpler way to do this, but so what I'm going to do here is loop through all of the rows, all of the so this will actually loop through row I. All of the, so I'm going to loop through all the rows, and this, okay, actually this is the same logic as before. Where is it? Here, row of I is the same idea. So this will be column I, and this will be box I. Okay, so all right, so if there is a okay, so we're figuring out, so here what we're figuring out is how many numbers are already solved in this row, this column, and this box. Okay, so you see here, if we have found a solved entry, we update the number of squares that are solved in this row by 1. So, like, you know, the best scenario would be that there are 9. Like, row count is 9, that means that we have solved everything in this row. Right? If row count is less than 9, that means that there is at least one unsolved entry in this row. Okay, so we have went through every single box, every single row, and every single column. And we have, so some of the rows, columns, boxes could be fully solved. Their row count would be 9. They would not have made it into this dictionary. So this dictionary has all of the unsolved rows, columns, and boxes in it. And what we're going to do is we're going to take the row, column, or box, which is the closest to being solved. Okay. And that's where we're going to make our guess. Okay, so this, okay, so if you see here, we are taking the, so this is the type. T is type, so T is going to be like R, C, or B. It's just some way that I keep track of, is it a row, a column, or a box? And I will be the actual, the number. So it will be like row 1, row 2, row 3, etc. Actually, it will be like row 0, row 1, up to row 8, and so on. So that's what this is. Okay. So if it's a row, we're going to go through all of the, so we're going to go through all the entries in this row, column, or box. All right. So the minute that we find a entry in this row, column, or box that is unsolved, we're just going to use that as our guess. Okay, so this pretty complicated method, in the end, all it is doing is scanning all of the rows, all of the columns, and all of the boxes. And it's looking for which row, column, or box is closest to being solved. The one that is closest to being solved, that's the one that we're going to make our guess in. Okay, so for example, if we find a row where 7 entries are solved and there's only 2 unsolved, we're going to make a guess in that row, column, or box. Okay. And then, so now that we know which row, column, or box we want to make a guess in, we're just going to loop through that row, column, or box. And the minute that we find an unsolved square, that's the square that we're going to make a guess in. So the square will be like that square, and the options will be all of like whatever we wrote in the top left-hand corner. So hopefully, like, just there's 2 options here. Okay. So we break, and it's the same logic for the column. And once again, we have this strange looking method for looping through this box, but it's similar to what I described before. You're just trying to achieve this sort of zigzaggy thing. All right. That's why you have all these like divide by and mod. Okay, so when we are returning our guess, we're going to return the square, whether it's a row, like what row, column, or box it is. So this would be like we're making a guess in row 9, this square, and these are the possible guess options. Okay, so believe it or not, we're actually done. This is the entire solve algorithm. So I'm just going to quickly go summarize what we've done. So we have First of all, we have a backtracking strategy, which involves having like our root node, applying some solve strategy. If the solve strategy works perfectly, which it probably will for some very simple puzzle, you don't even need to worry about any of this. All right, and we're done. If you get stuck, then you need to make a guess. And you store the previous board in case you need to roll back to it and when your guess is incorrect. You may need to make several guesses. Every time you make a guess, you reapply your solve strategy. You go as far as you can go. You solve as many squares as you can until you get stuck again. If you ever fail, you go back and change your previous guess. That's the idea for the backtracking. For the solve strategy, we are going through every single box and we are filling in the top left hand corner all of the missing entries. Like for every square, what are the possible numbers that could go in the square? And then we will solve as many of those as we can. If we do that for all the boxes and we weren't able to solve anything, we're stuck. And then, but assuming that worked, then we're going to check, are we solved? Like, is there anything left to solve? If there isn't, we're done. If there is stuff left to solve, we're going to do this whole solve strategy again. And it may fail, like if we find a square where there's some like impossibility, like there's nothing that could go here that would work, so we're stuck. And like we failed. Okay. And so the solve missing entries, this function is, so we've already, okay, so fill missing entries is filling in the top left hand corner everything that could go in this square. Solve missing entries is like we've already filled in everything and now we just like determine are there any squares we can actually solve. And get possible values is just like figuring out what are all the possible values that could go here by scanning the rows, scanning the columns, and scanning the boxes. Okay, so it looks like in the end this took me almost 40 minutes, so didn't quite achieve my 30-minute time, but that's everything. So thanks for watching, and I will also be posting a C++ solution in the description for those interested. Bye.